Hello, my name is Ciera Hudson, and I'll be discussing the circuits and capacitors experiment. In this lab report, I will be analyzing the behavior and values of different circuits modeled virtually. I used Java to create virtual simulations of two different circuits using resistors and capacitors. This will allow us to analyze how the circuits would perform in real life and describe the motion of electrons over time. I will also predict important values in the circuits, including conventional current and change in voltage over parts of the circuit, and validate them using a virtual voltmeter and ammeter that are provided in the Java simulation. Lastly, I'll be answering a couple of conceptual questions to further our knowledge of circuits and their real-life behavior. Let's talk about the concepts that will be used in this lab. The first one is Ohm's law, which is probably the most well-known circuit law. It states that the voltage across a resistor is equal to the current moving across it times the resistance of the component itself. This equation can also be rearranged to solve for each value. The next important concept is the loop rule, which defines the fact that the total voltage in a loop, or simple circuit as shown in this lab, must be equal to 0. The last rule that is relevant for this lab is the node rule, showing that the sum of all of the current moving into a node, or a junction of multiple wires, must be equal to the sum of all the current moving out of that node. This image shows a simple node and how the node rule can be applied when looking at a circuit diagram. The first circuit that I'll be analyzing consists of two 1.5 volt batteries and two resistors, one 47 ohm resistor and one 100 ohm resistor. We can actually predict the current moving through this circuit. Because the circuit is in series and not parallel, we know that the current will stay the same throughout the entire loop, so we can solve for it using Ohm's law. The total voltage in this circuit is equal to 3 volts, which is the sum of the voltage of both batteries, and the total resistance is 147 ohms, which is the sum of the values for each resistor. Solving for the current in this circuit, we can predict that an ammeter should read 0.02 amps when placed in different locations within the circuit. Now let's take a look at the circuit simulation. As you can see, in each image of this circuit, there are two batteries on the left and two resistors on the right of the loop. When an ammeter is placed at both the top and the bottom of the circuit, we can read that the current stays the same and is equal to the prediction that we made on the last slide. The picture on the right shows how a voltmeter is used to measure a change in voltage. This picture shows the change in voltage over two batteries, which equals 3 volts. In the next slide, we'll analyze how that voltage changes as electrons run through the circuit. Here, you can see a graph of voltage over the length of the circuit. At the bottom of the graph, the symbols for each component of the circuit are shown for clarification. The image on the right shows each section of the diagram as it corresponds to the graph. As you can see, the two batteries cause a voltage rise of 3 volts since they are each equal to 1.5 volts. Over the 47 ohm resistor, the voltage drops by 0.959 volts, which is actually equal to I times R, or 0.2 times 47. Over the second 100 ohm resistor, the voltage drops by another 2.041 volts, which brings the voltage back down to 0. This means that the loop rule is satisfied, as the total voltage around the loop is equal to 0. The second circuit that I'll be analyzing consists of one 9-volt battery, a light bulb of either 10 or 20 ohms, and a 0.2 farad capacitor. The reason that I'm including two different resistance values for the light bulb is so we can address the change in current over time due to the capacitor and the difference in resistance of the light bulb. This picture shows the appearance of the circuit simulation in Java. On this slide, you'll see that the brightness of the light bulb depends on the state of the capacitor and if the battery is connected within the circuit. First, let's discuss how a capacitor works. When the circuit is first connected, the capacitor does not affect the flow of the circuit. Instead, it acts as a short, and current can pass through smoothly. However, as time goes by, charge builds up on the plates of the capacitor and current decreases, causing the light bulb to dim. When the capacitor is fully charged, it completely prohibits electron movement and the current is equal to 0. This means that the light bulb is no longer glowing at all. Once the battery is removed and the circuit is reconnected, the capacitor begins to discharge. Current once again flows through the circuit and the light bulb is on again, but once again begins to dim. As the capacitor finishes discharging, the current moves back down to 0. In this table, I recorded the time that it took for the capacitor to completely charge and discharge. The values in the table correspond to the different light bulb that was present in each simulation. As you can see, it took about twice as much time for the capacitor to fully charge and discharge when the resistance of the light bulb was doubled. It also took about the same amount of time for the capacitor to charge and discharge in each scenario. The first conceptual question that we were asked to answer is what would happen if we performed this lab in real life and used an actual ammeter instead of an ideal simulated ammeter. The answer to this is that ammeters can hold an amount of resistance in real life, which would change the value of the reading. In this case, it would read a current value that is slightly lower than it actually should be. The second question asks what would happen if we were to use a battery to charge a capacitor in real life. How would the charging and discharging of the capacitor compare to the ideal model that we created in the circuit simulator? Well, like the ammeter, a battery in real life can hold a small amount of resistance, and it also wears down over time. This means that the ability of the capacitor to fully charge will be affected. In addition, the current over time in a circuit with a capacitor is asymptotic, so it will never actually charge completely. In this lab, we were able to predict current and voltage in 2 different virtual circuits and verify our predictions using virtual multimeters and ammeters. We described the behavior of a circuit with a capacitor present and compared its timing based on the resistance of a light bulb. Lastly, we answered a couple of questions that helped us think about the way that circuits behave in real life and how it would differ from our ideal version of a circuit. Thanks for watching!